Oh, yes.
Yeah, okay. So for the second talk of today, we have Thibaut Poiré from the University of St. Andrews, and then today is going to talk to us about spaces of roots and combinatorics. So yeah, let's start.
And I should specify now, even if it's written, that it's joint work with Margherita Mello, who is in Rome. And I'll start by picking an integer r, and this will be the r such that we want to look at rth roots of things. And the things are going to be line bundles on curves. We're going to work over C, but this is not really important. You could do some version of the same thing above any base scheme on which the integer r is invertible. Right? So it doesn't have to be a field, it doesn't have to be local, but all the residue characteristics are not allowed to divide r. Right? So if we want to do roots of line bundles on curves, we first have to talk about curves. So many of you might know this guy, but let's introduce it. If you take smooth curves, so over C, this means Riemann surfaces with a bunch of markings, so distinguished points of them, there is a space that parameterizes these pictures, and it's called MGN. Here, G is the genus, so it's the number of holes. Here it would be 2, and N is the number of marked points. So for each choice of integers G and N, satisfying some condition, you get a space MGN like that. And points of MGN are these pictures, and deforming the picture a little bit corresponds to moving a little bit on MGN. Curves are everywhere and important, and this means that MGN is also everywhere and important. And so there's a big field of research which is dedicated to trying to understand things about it, right? What it looks like computing geometric invariance. The first few things we can say that are not too hard is that its dimension is 3g minus 3 plus n. So it's easy to see, for example, that there is a term in plus n because each time you add one distinguished point, you're choosing one more point on a curve, which is one-dimensional. So you increase the dimension by 1. The 3g minus 3 is less obvious, but also not too hard. This is a smooth space. I didn't write it, but it's irreducible. But it's not proper. And the reason for that is that if you take a bunch of smooth curves in a one-parameter family and you try to find a limit for them at some critical value, sometimes the limits, I put this in quotation marks, wants to not be smooth. Here's an example by picture. Take this sort of elliptic equation, y squared equals this degree 3 polynomial in X inside the projective plane. And it's pretty well known from the theory of elliptic curves that if the polynomial in X has 3 different roots, this is a smooth elliptic curve. But if 2 roots become the same, this acquires a singularity, right? So an example here, if t equals 0, then the polynomial in X has a root at 0 with multiplicity 2, and you see this nodal singularity at the origin. The fact that I found a family with a singularity at the origin doesn't mean that you couldn't find another family which is smooth at the origin, but in this example, it's not too hard to see that this also doesn't exist because the discriminant of the equation up there is t, and the discriminant always has to be non-zero if you want to be a smooth elliptic curve. Okay, so MGN is not proper, and this turns out to be quite annoying because we have a lot of tools in algebraic geometry that we only know how to apply to proper spaces, right? Things like intersection theory. One way to sort of save the usefulness of these tools and still use them is to embed a non-proper space into a proper one. use all the compact tools on the proper one, and then try to deduce things about the subspace, right? So if you have a space M which is not proper, you have to try to find a compactification M bar of it. And this means put M inside M bar via a dense open immersion. There's many ways to do that usually, but we want one that is not too ugly, right? We want to still be able to understand M bar. So we want it to keep as many of the good properties of M as possible. Fortunately, this has been done for MGN. Dilling, Mumford, and Knudsen have proven a while ago, in the 80s, I think, that you can compactify MGN by another parametrizing space. And this one parameterizes curves that are allowed to be a little bit singular. They're called stable curves. And what a stable curve means is two things. Oh, yeah. And it keeps a lot of the good properties of MGN. It's still smooth, it's still irreducible, but now it's also proper. Yeah, so I was saying I need to tell you what a stable curve is. And a stable curve is a curve that at every point is either smooth or has a nodal singularity, meaning that locally it looks like the intersection of two lines with equation product of two parameters u and v equals 0. And if you want to be stable, you also have to ask that the curve, considered as a curve with its markings, has finitely many automorphisms. And this condition can be made very explicit. Your curve now may have a bunch of components intersecting transversally at nodes. And for each of these components, you look at the genus of the component. And if it's 0, you need at least 3 special points, so nodes are markings, to rigidify the automorphisms. And if it's genus 1, you need at least 1 marking. And this is because the automorphisms of P1 are 3 transitive. They can bring 3 points anywhere. And the automorphisms of a genus 1 curve are transitive. Okay, so the same example we had earlier becomes a stable curve if I mark 1 point because it's genus 1. And because the singularity of the singular fiber is a node, right? You can find coordinates u and v such that locally the equation is uv equals 0 and the coordinates are those that I've written down there. Okay, so as we've explained a little, a stable curve is essentially made of smooth curves which intersect transversally at a bunch of points. And this means that I can encode all of these intersections of components into a graph, which I'm going to call the tropicalization or the dual graph of the stable curve. The vertices of this graph are the irreducible components of the curve. The edges of the graph are the nodes of the curve, and so they join the two components that are touched by the node. And there's also what's called legs of the graph. That means edges that are attached to only one vertex, and those correspond to the markings, the distinguished points. Here's an example. I have a stable curve drawn on the left. I have its dual graph in the middle, so you can check there's one vertex per component and one edge per node. You can see that the C4 has a loop because the component has a node with itself. And you can see that if I give you the marked components on the right and the graph in the middle, you can reconstruct the curve on the left. Oh, I forgot a marking on C4. And this means that the space parametrizing stable curves, MGN bar, has some sort of recursive structure, right? If I look at the boundary, so the set of curves in it that are not smooth, it's partitioned by graphs, right? I can look at the subspaces in MGN bar where the dual graph is of a fixed isomorphism type. And for each piece of this partition, I can cover that piece by a bunch of smaller MGN bars indexed by the vertices. This basically means consider all the normalized irreducible components as smooth marked curves themselves. And I say that this is a cover and not an identification because sometimes two of these pieces of data can be identified by an automorphism of the graph. So this is an action that has to be rigidified. Right. So why do we like MGN bar? Well, there's a bunch of reasons. First, it's a compactification that still has a lot of the good properties of the original space. It's still smooth, it's still reducible, it still parameterizes objects that we can wrap our heads around. You can use this recursive structure at the boundary, right? This partition into pieces made of smaller MGNs to turn theorems about MGN bar into theorems about MGN. And you can use what's called degeneration techniques on it. So I'm going to explain what that is now with a drawing. The idea of degeneration techniques is you start with a smooth curve of high genus, and this can be a very complicated object, and you want to prove something about it. You have to do some hard algebraic geometry, and imagine that you can't, but imagine that you draw a path inside MGN bar from the point corresponding to this curve to another point, this little s, that lies very deep in the boundary. And imagine that your problem has some topological niceness such that you get to bring it with you along this path. Then you can turn your question about the curve C eta into a question about the curve CS that is at the boundary. And if you go really, really deep in the boundary, because the total genus of a stable curve is the genus of all the components plus the genus of the graph, so the rank of the homology of the graph, eventually you can reach a curve which is just made of a bunch of P1s glued with instructions given by a graph. So you can take a very hard algebraic problem and you can turn it into a problem about P1 and about the combinatorics of graphs. And often that's easier to solve. So you bring your problem to the boundary, you do the math there, and then you bring the solution back with you along the same path. Okay, so that was a quick intro to MGN bar. And remember, we want to do roots of line bundles on curves, so we also need to talk about line bundles. So if you start with a smooth curve and you look at the Picard group parameterizing line bundles on it, it has a degree map to Z, and the kernel of that degree map is a very nice topological group. It's an abelian variety, meaning that it's a group object, it's representable by a scheme, and it's proper. And these are very restrictive conditions, and they're really nice objects to work with. Right, so it fits in an exact sequence like this. And this works well with respect to families of curves. So we also get a universal Picard group for the universal curve of MGN bar and a universal Jacobian, which you should think of as a family of abelian varieties. So it's an abelian scheme over MGN. Right, so as a morphism, this is smooth, and all of the fibers are proper groups. Now, if I look at the Picard group of any smooth curve with markings, I can name a bunch of special elements in it. The first thing I can do is I can always look at the tangent bundle and at its inverse, the cotangent bundle. Because the curve is smooth, this is really a line bundle. For each of my markings x1 to xn, I can look at the line bundle O of xi. These two always make sense. And I can, of course, take linear combinations of these things. So I pick integers k and m1 to mn, and I look at the line bundle omega to the power k tensor O of my linear combination of markings specified by m. So I'm going to use this notation a lot. I'm going to call these guys omega k of m, and this is a lattice of rank n plus 1 inside the global sections of the universal Picard group, right? Because they make sense on every curve. So because they give me global sections of the universal Picard group, it means that I can now introduce the space of roots I wanted to talk about as parametrizing smooth curves with markings and with the rth root of my favorite omega k of m. So from now on, I'm almost for the whole talk, I'm just going to fix one omega k of m, and I look at the rth roots of this one. Okay, this gives me a moduli space. It has a forgetful map to MGN bar. And I'm just gonna forget omega k of m in the notation, and I'm gonna write it as 1 over r smooth. So I care about these guys, but I want to tell you a couple words about why you should care about these guys. The most important example probably is square roots of omega. And these really appear in a surprising number of geometric contexts. The enumerative geometers care about them. So the people who want to count curves of a certain type inside spaces and try to understand mysterious spaces via these curve counts. Sometimes, for geometric reasons, they also end up with counts of curves with a spin structure. They appear in theoretical physics somehow. Don't ask me why or how, but this spin is the same as the spin of electrons for string theorists. And sometimes in number theory, you also see square roots of omega appear. I know relatively little about that as well. What I do know a bit more about is Hurwitz theory. So Hurwitz theory is the study of maps from curves to P1 where you control where the ramification happens. So you demand that the map to P1 is only ramified at the markings of your curve C, and you also want to impose how much ramification happens. So you're going to say, oh, I want my ramification index to be 3 on the first marking and 4 on the second and 6 on the third, and then 1 everywhere, something like that. Once you do that, if I give you one ramified map like this, and you pull back O of 1 from P1, which is a square root of the trivial bundle, which is also the tangent bundle, what you get, depending on which ramification profile you've chosen, is square roots of various twists of omega at the markings. And this means that if you look at the Hurwitz space of all the maps F like this with a fixed ramification profile, this has a map to a space of roots, right? Because universally, you can pull back the O of 1 on P1 and get a root of some omega of m. So because you have a natural map between these two moduli spaces of interest, every time you can say something about one, you can say something about the other. There's a nice interplay between their geometry, and you can use one problem to solve the other, and vice versa. And last but not least, for the same reason, essentially, because spaces of roots have a forgetful map to MGN, and their compactifications have forgetful maps to MGN bar, you can use them to understand MGN bar. So this is very important for the people who care about the tautological cohomology of MGN bar. What that means is on MGN bar, you have a bunch of natural cohomology classes. You have some coming from the boundary strata. You have some coming from the markings themselves, which are divisors on the universal curve. So there's a bunch of classes you can name because of the modular interpretation. And if I give you a linear combination A and a linear combination B of these classes, a priori, it's not obvious when A equals B, right? It's not obvious what the relations are. And it turns out the people who have found the relations between these interesting classes, they did that by using the meaning of spaces of roots, making sense of some classes on spaces of roots and pushing them forward and deducing relations. No, so hopefully this is enough motivation for now. And let's start talking about the actual geometry of the space of roots. The main thing I want to do today is compactify it and tropicalize the compactification. So the first point is pretty self-explanatory, right? We want to do what we did to MGN, which is we want to put the space of roots into a proper space. We want this proper space to be as nice as possible. So we still want it to be modular. We still want it to be smooth, etc. And then we want to tropicalize it, and this means exhibiting a recursive structure. So the same way we did it with MGN bar and with stable graphs, we want to show that this space of roots has some recursive structure at the boundary, which is guided by some combinatorial objects. We want to be able to name a bunch of discrete geometric invariants analogous to stable graphs, such that the collection of these invariants sort of, packages the recursive structure of the boundary. I'm going to make a little simplifying assumption that the degree of omega k of m is 0. This is really only for exposition. It doesn't matter very much. And the reason it doesn't matter very much is if you think of the degree of the universal bundle, if it's not a multiple of R, then of course the space of roots is empty, because if you want to have an Rth root, your degree also needs to have an Rth root. And if the degree is a multiple of R, then you can just twist all roots by some multiple of, let's say, the first marking. And this makes the degree of the root get a -1, and it makes the degree of R times the root get -R. And so you find an isomorphism between your space of roots and a space of roots of degree 0. Okay, once you've done that, by definition, the space of roots maps to the Jacobian, because the Jacobian was line bundles of degree 0. So we found a map from our interesting space to a universal abelian variety over MGN. That's the point of this extra hypothesis. And we know that roots inside the Jacobian form a torsor under the torsion of the Jacobian, and that makes S1 over R smooth a cover of MGN of degree R to the 2G, right? Because as an abelian variety, the Jacobian has dimension G. If you're a complex geometers, abelian varieties of dimension G are essentially C to the G modulo a maximal rank real lattice. And so as a group, this is R to the 2G modulo Z to the 2G. Right? So the torsion has exactly this order. Okay, and now we run into the same problem we had with MGN, which is that both of these things are fibrations over MGN with proper fibers, but they have no chance of being proper themselves because the target of this fibration is too small. So if we want to apply degeneration techniques and intersection theory and all these nice mathematics that we know how to do on proper spaces, first we need to find compactifications. And same as always, the game is to find compactifications which are nice and which play nicely with the ones we already have. So we would like these compactifications in red to have forgetful maps to MGN bar. We would like them to have good geometric properties. And most importantly, we would like them to still be meaningful, right? So we want to find the correct way to extend our moduli problems from MGN to MGN bar. Your first instinct maybe would be to say, oh, if what we had here was line bundles of degree 0 on MGN, on the curve over MGN, why don't we let this red LP thing be line bundles of degree 0 on the curve over MGN bar? And the problem is that this does not give you a compactification. Right, so I'll hammer down that point. The pig 0 of the universal curve over MGN bar is not proper. So we need to find something to replace it. Here's an example. If I give you one of the nodal cubics of earlier inside the projective plane, remember, right, this was an irreducible rational curve forming a loop with itself. Well, the Picard group of that thing is the multiplicative group. Why is that? Because if I normalize, I get P1, and the only line bundle of degree 0 on P1 is the trivial bundle. So now let's undo this normalization process. Let's try to glue the trivial bundle on P1 to itself. This means I have to give an isomorphism between the fiber at the first preimage of the node and the fiber at the second preimage of the node. I have to tell you how to glue two lines, and that's exactly the same thing as giving you a complex number. Okay, NGM is not compact. Now let's look at the details of this failure of properness a little more. Look at a picture like this, where I give you a family of curves over spec C double bracket T. So the double bracket is to avoid problems further in the affine line, but basically you should look at a family of curves over the affine line. And suppose that the generic fiber is smooth, for example, this smooth elliptic curve here, and the special fiber is one of my nodal cubics. And notice that there's a little difference with the previous example. Now in my equation, on the last term, I have an x squared minus t to the power 3. Okay. So the local equation at my node z is parameter of one branch times parameter of the other branch equals t to the 3. And now, because of the evaluative criterion for properness, if the Picard was proper, this restriction map from pick of the whole family to pick of the generic fiber would be a bijection. And what I claim is that it's not surjective and not injective. So first, it's not surjective because as I just said, the local equation for the total surface C at this node is product of two parameters equals t to the 3. And this is not a regular equation. So what I have is a singular surface. And when I give you a singular surface and a line bundle away from some problematic divisor, if the divisor contains the singularity, I can have problems extending the line bundle to the singularity. So the solution to get rid of that is to blow up at the singularity first to get a regular surface. In this example, I'm introducing by blowing up two exceptional divisors in red and in green at the special fiber. This means instead of my one node, I now have three nodes. And at all of them, the local equation is now the regular one, uv equals t. In a sense, this solves my surjectivity problem because now the restriction map of this blow-up C prime is surjective with the same generic fiber. Okay, so we would like to say replace C by C prime and your troubles have gone, but they haven't gone. This map is also not injective because if you look at any of these three components of the special fiber, E1, E2, and C1 prime, this is now a Cartier divisor on the total surface, so it gives me a line bundle. And because the Cartier divisor does not meet the generic fiber, this line bundle is of course trivial on the generic fiber. So for each of these divisors, I get a line bundle in the kernel of the restriction map. And some of them are non-trivial. The only trivial one is the one that has the same multiplicity at all three components. Okay, so first we blow up the curve, then we mod out this kernel, and then we've solved both of our problems. And this suggests that instead of the picks of stable curves, the correct moduli space we should be working with is what's called the logarithmic Picard group, which I'm taking some liberties with the truth here, but you should think of as a limit over nice blow-ups of the curve of quotients of the Picard group by these kernels that we've just seen. I'm going to leave that on there for a few seconds. So C prime to C is a nice blow-up, and this PL is the kernel we've just identified. It's O of a Cartier divisor, which is a combination of components of the special fiber. Okay. Now, a little technical point. If I want to tell you how much to blow up, and if I want to tell you what this kernel we have to mod out is, it was very important in the previous example that I had access to the smooth generic fiber C eta, right? Because I needed these local equations uv equals t to the n. Because what happened to the special fiber is not a blow up, right? What happened to the special fiber is mysteriously, I started with a nodal curve and I got a new nodal curve with a bunch of extra P1s. And without having access to these local equations, I don't know how many P1s to put there. And same thing, if I just had a nodal curve and nothing else, I wouldn't be able to take a component and extract a line bundle out of it, right? I need an ambient space in which this is the normal bundle. So I need these local equations uv equals t to the n. If I just have a pre-stable curve, the equation is uv equals 0, and neither my solution for the existence problem nor my solution to the uniqueness problem work. So this complicates the problem, and this is sort of why there's a vast area of the study of compactified Jacobians because you cannot do this in the world of schemes. If you just have a pre-stable curve, there's no log-Picard group attached to it. There is one in what's called the category of logarithmic schemes, which is schemes with a bit of extra data. So we need to force the pre-stable curves to remember local equations uv equals something. Right, so as I just said, it's a scheme with a bit of extra rigidifying data. And in our example, if I look at the special fiber of the family CS2S as a scheme, this just has equation uv equals 0 at the node and I'm stuck. But as a log scheme, what happens with this extra bit of rigidifying data is I get to force the point S, the complex point S, to remember some formal parameter T. And I get to force the nodal special fiber of my family of curves to formally remember the local equation product of the parameters of the branches equals T to the 3. And then I can simulate what happens to the special fiber when I blow up and I know which line bundles to consider. So there is a log-Picard group. Okay, so this might seem a little artificial, but I want to try and convince you that there's something really deep going on here. And Fumiharu Kato will help me convince you because he's proven that pre-stable curves can always be equipped with natural log structures. So this process I just described of forcing the fiber to remember local equations for smoothings always makes sense on a pre-stable curve. And when you do that, the curious phenomenon is that in this category of log schemes, so schemes with a bit of extra data, this singular object now behaves as if it was smooth. So if I look at the infinitesimal lifting criterion for smoothness in the world of schemes, my pre-stable curve does not satisfy that. But in the category of log schemes, you write down the exact same categorical criterion, and now it looks like the pre-stable curve is smooth. So we're going to give a name to these curves with these natural log structures. We're going to call them log curves. And because of this theorem of Kato, we can now give another interpretation to MGN bar. Earlier, it was parameterizing stable curves, but now it parameterizes curves which are smooth in the world of logarithmic schemes. Okay, and it sounds like these are synonymous, so I've made no progress. But I really have, because of the meta-conjecture of log geometry. There's a little self-depreciating joke that log geometers like to make in talks, which is, oh, I've taken this big, famous, successful theorem, I've put the word log in 5 places, and now I call it my theorem. And that's the meta-conjecture of log geometry. You take something true about the geometry of smooth objects, you try to find the correct analogues in the category of logarithmic schemes of all the concepts in T and in the proof of T. You prove the theorem log T, drawing inspiration from the proof of T. So I'm being a bit caricatural, right? Sometimes one of these steps is really hard. Sometimes they're both really hard, but sometimes it works. And what tends to happen is because smoothness in log schemes is less restrictive than smoothness in schemes, the theorem log T now tells you something about how to extend T to singular objects. It's sort of the right way of degenerating smooth objects to smooth objects plus combinatorics and mixing the two kinds of math in the right way to describe what happens when you degenerate the theorem T. An example of that is that log-smooth curves are the same thing as smooth curves and the combinatorics of their dual graphs, maybe with an extra something to remember the equations appropriately on the graph. And so constructions over MGN which use the notion of smoothness often extend to logarithmic constructions over MGN bar. And that's particularly interesting in the case of MGN to MGN bar because it gives you compactifications of moduli spaces. So I'm getting ahead of myself, right? Here's how you compactify PGN logarithmically. It has been done by Molcho and Wise a few years ago. You start with a log curve. You can make sense of its log Picard group. And Molcho and Wise tell you that this log Picard group is log smooth over the base. It has a degree map to Z compatible with the degree map on PIC. The kernel of this degree map, the logarithmic Jacobian, is proper. The natural map from PIC is an isomorphism if the curve is smooth. So in the world of smooth curves, there's no difference between PIC and log PIC. And these 2 points together, the last two, already tell you that the universal log PIC is going to be a compactification of PIC, right? And the log Jacobian is going to be a compactification of the Jacobian because they coincide over MGN and log PIC 0 is proper. And you can, so the way smooth geometry is shuffled with combinatorics here is given by this exact sequence. 0 goes to the PIC 0 of the stable curve. This means line bundles of degree 0 on every component, not just globally. 0 goes to PIC 0, goes to log PIC, goes to this tropical Picard group. I'm not going to tell you what this is, but I'm going to tell you that it's a tropical object. It's a combinatorial object, so it's very nice to work with. It's all combinatorics. And yeah, this is the big theorem telling you that log PIC is well behaved. There's a bit more that is true. This logarithmic Jacobian, the degree 0 part, is a log-abelian variety in the sense of Kajiwara, Kato, and Nakayama. And I unfortunately don't have the time or willingness to explain what that means, but basically it's the right analog of abelian varieties, right? So abelian varieties in the world of schemes are smooth and proper groups, and that turns out to have very drastic consequences. And when you go to log schemes, now there's a few more smooth proper groups. And so the correct analog of abelian varieties are objects that are really rigid and well-behaved. So Kajiwara, Kato, and Nakayama have talked about those a lot. I'm going to let you process this for a second. Okay. So now we've defined log PIC, and we've seen that we get for free a compactification of PGN out of it, right? All we have to do is look at MGN bar, look at the universal curve, see it as a logarithmic curve, and consider its Picard group, its log Picard group. And now, because this is proper, and it has a map from PIC, I can make sense of my universal bundle omega k of m inside it, and I can take its rth roots, and I can look at its space of rth roots. So out of this compactification of PIC, I also get for free a compactification of the space of roots. So we have found red arrows. to compactify our diagram. The vertical arrows in this diagram are compactifications, and now remember, right? We want the compactifications to be modular. We also want them to preserve the good properties that the original objects had. This definitely happens here because my compactified space of roots is still a group torsor under a group under the torsion of logpic, which is still a finite group and still in some sense étale, right? Étale in the category of logarithmic schemes. So in particular, it has the same order, finite order that S1 over R smooth had. Okay. Now we've defined the space and we want to compactify it. Oh, sorry. We've compactified the space and we want to tropicalize it. And tropicalization, I'm not gonna necessarily formally say what it is, but it means extracting all the combinatorics you can extract. We've already seen a few examples. If I take a stable curve C, I can extract a dual graph out of it, and so that's the tropicalization of the stable curve. If I take line bundles on stable curves, what combinatorics can I extract from that? Well, on each irreducible component, my line bundle has a degree. So I get one integer per component of the stable curve. And this is equivalent to one integer per vertex of the dual graph. So I write it here as Nero-Severi is, sorry, Z of the vertices. And the reason we are taking a free group of the vertices here instead of Z-valued functions on the vertices is this is really not an arbitrary choice. It has to do with families. Imagine I give you a family of curves. It gives me a family of graphs where the graph of the generic fiber is obtained by contracting a bunch of edges from the graph of the special fiber. And it turns out these Nero-Severi groups are compatible with that operation, right? Because my degree on the generic fiber is the sums of the degrees on the special fiber. And this works well with more complicated generic graphs, right? One vertex upstairs is going to correspond to a subgraph downstairs, and I have to sum the degrees on each vertex to get the degree on that top vertex. Maybe I should have doodled that instead of trying to do it by voice, but the bet is made. Last but not least, if you want to tropicalize lockpick, you can. You can do it and you get an object that is a group as well. It only depends on the dual graph equipped with some sort of metric. And I'm not going to give you an explicit description of tropic, but you can, and it's all graph cohomology. I will say one thing, which is that the torsion of tropic, so tropic has a lot to do with monodromy, and therefore it has a lot to do with cycles. And in particular, the torsion of tropic is the first homology of the graph modulo r times the first homology of the graph. So it's a lattice of rank genus of the graph tensored with z mod rz. In particular, if I take my same omega k of m as usual, I map it to tropic and I try to look for rth roots there, they're going to form a torsor under this torsion subgroup. And so I know exactly how many I have, right? I'm going to find R to the H1 of gamma roots inside tropic. If you compare that to the R to the 2G that I had earlier, you can see that for each tropical root, I still have a lot of logarithmic roots. And in fact, you can do the math, and it turns out if I fix a tropical root, over that tropical root, I have the number of scheme-theoretic roots I have is exactly the number of roots inside the Picard group without a log. This is because, imagine my tropical root is 0. If you want to find a log root above 0, it exactly means finding a root in the Picard group. Okay, so that was tropicalization. And now on to the space of roots itself. I want to extract as many combinatorics I can from the problem. Well, if I give you a stable curve with a root on it, the first bit of combinatorics I can extract is, of course, the dual graph of the stable curve. So whatever my tropical objects are, they should live over tropical curves, meaning they should live over dual graphs. Meaning that the most natural way I have of trying to find my combinatorics is first take the partition of MGN bar by stable graphs, pull back that partition to the space of roots. In MGN bar, all of these pieces were connected, but in the space of roots, they have no reason to be connected. And every time I identify one connected component of one of these pulled back pieces, I've actually named more geometric discrete invariants than before, right? I had a very coarse thing, the dual graph, and I have found something more refined, some more refined invariant. So this is what we're going to take as a definition for now, right? The tropicalization of the space of roots is simply going to be the big complex made of all the connected components of all of these pulled back strata. So first couple remarks. Of course, because S gamma is always a cover of M gamma of the same rank, R to the 2G, that's the absolute maximum number of connected components I could ever have, and there's probably a lot less. Right? That's my number of roots, and two roots are in the same connected component if and only if they can be exchanged by the monodromy action of M gamma. If we want to know exactly what the set of components is, there's two games we need to play. The first is naming discrete invariants. Every time I find a function to some discrete space, I can use the fibers of this function to partition my space into open and closed subsets. And so I can bound the set of connected components from below, right? I have at least as many components as non-zero open and closed pieces I've found. And the second game is, once you've played the first game enough, you want to prove that all the pieces you've found are connected. And if you want to prove that these pieces are connected, you have no choice. You have to take all the roots with the same invariants and find some sort of path between them. Right, so the second game is to construct explicit deformations between roots of the same invariants. A simplified version of the game is we're going to first suppose that the graph is trivial. It's just a vertex with a bunch of markings and no edges. If the graph is trivial, it means I'm working over MGN, and it means I'm trying to compute the components of the space of roots smooth. And that's the same thing as the connected components of the total space of roots because of some smoothness argument. Right, so the next theorem, which is the first I want to present, solves this problem. It computes the connected components in a bit of a roundabout way, so I want to stop on it for a second. First, we introduce some numbers depending on the problem. D prime and D are the GCDs of R and of these coefficients that appear in the universal bundle. So these are numbers depending on the universal bundle. And now I'm going to look at the sequence of multiplication maps going from R-th roots to D prime roots to D-th roots. All of these maps are surjective. And so if I want to understand the components of the left-hand side, what I can do is understand the components on the right-hand side, understand whether they split or not when I pull them back along the first map. This tells me what the components in the middle are, and then I do this again. So that's what we're going to do now. The components on the right-hand side are classified by this point number 1. The space on the right-hand side is actually isomorphic to the torsion. And so the torsion is a finite group. Every element of it has an order in that finite group, which is deformation invariant. And the theorem tells you this is actually the only invariant. You can always exchange two roots of the same order. Then when I pull back along the rightmost map, if D equals D prime, of course, nothing happens. And otherwise, you're going to split your component if and only if it has odd order, right? So even order stays connected, odd order becomes disconnected. And when you split into two. And finally, when I pull back along the leftmost map, this does nothing to connected components. Right. So put all these 3 points together and you've completely described the components of the space of roots. I'll also say verbally that this mysterious sign in Z mod 2Z is it's not just saying there's two things. This is a very meaningful geometric invariant. It was first identified with Kornalba, by Kornalba after all the work of Mumford. It has to do with quadratic forms on abelian varieties. I'm not going to get into the details, but the point is this is a meaningful invariant. It makes sense. You can extract it from some cohomology groups of your Jacobians. Let's look at a little example. Right, so my theorem should tell you how to count the connected components of this space of 4th roots of omega squared. Right? Let's go back to the theorem. If you want to understand the 4th roots of omega squared, the first thing you have to do is look at multiplication maps to simpler spaces. And here I get a simpler space by squaring. After squaring, I land in square roots of omega squared, and that's the same as the 2 torsion. The reason square roots of omega squared are the same as the 2 torsion is because I can just translate my roots by omega. Okay, so after squaring, I get a space which we know is partitioned between the trivial root, which has order 1, and the 3 non-trivial roots, which have order 2. And the theorem tells you actually the monodromy action exchanges every root of order 2. So these are really the two connected components. Now you can pull back these two components to the space of fourth roots, and you get open and closed subspaces of order 1 and 2, which may no longer be connected. One of them stays connected, which is the space of order 2, but the other one has two connected components, one of sign 0 and one of sign 1. And so in total, this space of fourth roots of omega squared has three connected components. And if I go back here, you can see that if you applied the same reasoning to roots of order 4 times 10 billion, you would still get only three connected components, because this phi r d prime does nothing to the connected components. Okay, so this was the trivial graph, and there's also non-trivial graphs. The first thing we can do, if I give you a graph that is not just a point with markings, is turn my space of roots into a slightly easier one by rigidifying automorphisms, right? So remember, S gamma was just roots on curves whose dual graph is isomorphic to gamma, and so there can be monodromy, which applies an automorphism of gamma, and I would like to rigidify that. So we can express this S gamma as a stack quotient, S gamma rigid modulo automorphisms of gamma, where S gamma rigid parameterizes curves with a root and with a fixed given isomorphism between their dual graph and gamma. So that means that the components of my curve are still allowed to move and deform, but now the configuration, the way they're arranged using gamma, that's not allowed to move. That's not allowed to have monodromy automorphisms. Because of this quotient presentation, once I understand the components of S gamma rigid, I can basically just mod out the action of out gamma, and I will get the components of S gamma. So let's compute the components of S gamma rigid. Again, this is done by playing the same two games. The first one is you have this space S gamma rigid and you want to name a bunch of discrete invariants on it to separate them into open and closed subsacks. And the second game is to show that all of these open and closed pieces are connected by constructing explicit deformations. Okay, so first game, how many discrete invariants can I find on S gamma rigid? The first thing is all of my roots have an image in the tropical Picard group of gamma, and this is a discrete group. Sorry, the tropical Picard group is not discrete, but the set of roots of omega k of m in tropic is definitely discrete, right? It's just a copy of z to the first Betti number of the graph, as we saw before. Z mod r to the first Betti number of the graph. So that's the first discrete invariant. The first theorem gives you another discrete invariant, right? My root has an order and sign pair, and this order and sign pair is just a bunch of numbers, so it cannot move, cannot deform. And the third one is a bit more involved, but it's sort of the same principle as what we did with orders. If I multiply my root by some sufficiently large integer, eventually it's gonna land in the subgroup pic, right, of log pic. And if I multiply it by an even larger integer, it's going to land in the maximal torus inside pic. So the pic of a nodal curve whose dual graph is gamma has a maximal torus, and this torus is a bunch of monodromies around the cycles of the graph. The reason is, take the trivial bundle on the normalization of your curve, use a monodromy map like this to describe how to glue the trivial bundle to itself at nodes, and you will get a line bundle. Okay, so multiply by a large integer r, you're gonna land in this maximal torus. You're in fact gonna land in the torsion of this maximal torus, and that's a discrete group. That's morphisms from some lattice to mu r. So this discrete group is actually made of discrete invariants on the space of roots. Right, that's three kinds of discrete invariants I have on S gamma rigid, but we're not done yet. All three of these invariants, I could also get copies of them on subgraphs if I had restriction maps from the space of roots on gamma to the space of roots on a subgraph, right? And this is not exactly true on the nose, but some version of it is true. If I give you a subgraph and I choose a fixed tropical root, then I get some sort of restriction map from roots of omega k of m on gamma to roots of some different universal bundle on gamma prime. The way to keep track of the multiplicities of the markings can be a bit subtle, and it depends on a choice of tropical root. But still, because the story I've told you earlier is valid for every choice of omega k of m, my discrete invariants 1, 2, 3 on gamma, I also get some versions of them on gamma prime attached to this other universal bundle. So by restriction, the invariants 1, 2, and 3 do still make sense on the subgraph gamma. Process a bit. And now the big claim is that this is all there is. So all my invariants, tropical root, order and sign pair, and monodromy map on every subgraph. Together, they form what I'm going to call a combinatorial type. Of course, there's some sort of compatibility relations between these invariants, right? For example, it's impossible to have order 1 if the tropical root has an extremely high order and things like that. But some of these combinatorial types are compatible. So we're going to say that a combinatorial type is realizable if there exists a root with all of the invariants in the type. It's a bit subtle, but we can understand completely when a combinatorial type is realizable. And the big theorem, well, I should say, I do say in progress, is that realizable combinatorial types do classify the connected components of the space of roots. Modulo automorphisms of the graph, right? So the realizable types, which we understand, classify the components of the rigid space of roots, And then I mod out the action of out gamma, and I get the connected components of S gamma. And so this means that we have successfully tropicalized our space, right? For this problem, the tropical object, the analog of stable graphs, is combinatorial types. Leave this on there a second because it's the main point I really want to hammer down. And then I'm just going to show you fun pictures. Well, first a fun lemma and then a fun picture. So I've talked a lot about invariance in this last part of the talk, and I've talked very little about deformations. I've sort of hidden the way we prove things. But once you found all these beautiful geometric invariants that give you combinatorial types, you need to do the work of showing that two roots of the same invariant can be, or in the same connected component, you can find a path from one to the other. And so you need to construct a bunch of deformations. One very useful fact, which in fact we use in the proof of the first theorem, is this lemma. Look at MGN bar. If you're inside the dense open MGN, the dual graph is very stupid. It's just a point. It has no homology. And as you go down deeper and deeper in the boundary, the genus of the components diminishes and the genus of the graph increases. Right? And you have a big closed subspace in MGN bar where the entire genus is eaten by the graph. So the graph has genus G, and all the components of every curve in there are rational. They're all copies of P1. This lemma says, if I look at the monodromy action of this M on the homology of the dual graph, which now is a lattice of constant rank G, actually the fundamental group acts via every linear automorphism. Right? So this lemma could be informally rephrased as MGN bar has a lot of monodromy. And the proof consists in essentially one drawing. Right. So you should imagine that these two graphs have genus G, right? Even if G is very large, I can generalize this example by putting more loops here and more loops here. So this family of two strata is inside M, and the stratum here lives inside the closure of the stratum here, because I get from this to this by contracting the two red edges. And that means that the monodromy action of M contains copies of the monodromy action of M gamma and the monodromy action of M gamma prime. Right? So whatever I can do to the homology of my lattice using pi1m is at least as much as what I can do using pi1 gamma and pi1 gamma prime. And the fundamental groups of gamma and of gamma prime act on the homology of the graph via automorphisms of the graph. So all I need to tell you now is why this graph and this graph together have enough automorphisms to obtain all of GL of H1. Well, if you look at the basis of homology consisting of these loops that you can directly see here, You get the same basis on this side by looking at all the G-2 loops here and these two cycles, which pass through the red edge. And you can see that automorphisms of gamma act on H1 by every permutation matrix in this basis, right? Because I can always exchange two loops using an automorphism. And I can also flip the orientation of one loop, and I get a diagonal matrix with a bunch of -1s if I want them. And in GL of Z to the G, that's every diagonal matrix. So this gives me diagonal matrices and permutation matrices. The only extra thing I need is one transvection to get all of GL of H1. And this graph gives me one transvection. Up to sign, I can exchange this red edge with the one on top, and you can check that this gives you a transvection. So this is an example of the sort of deformations you have to build when you want to identify your roots. In fact, this exact lemma we use to show that the substacks of a fixed order inside the torsion are connected. And this was the first point of the first big theorem. And there is one slide left, but it just says thank you for your attention.
Yeah, thank you. Are there any questions or comments?
So I just have one question. I mean, so we have sort of these combinatorial versions of MGN bar coming from like the sort of Pants decomposition with sort of a metric graph. And so I'm wondering if the tropicalization root construction, I mean, if there's any way to sort of interpret that in that framework, does that sort of make sense?
Yeah, I think so. But the interpretation is well, okay. The first thing to observe is that the combinatorial types refine the stratification by dual graphs, and so one geometric thing that comes with a combinatorial type is a pair of Pants decomposition of the universal curve, of the underlying curve. What the other invariants mean is a bit less straightforward, because basically all of these invariants have their own geometric interpretations, right? The order tells you an order of some multiple which happens to be a torsion element. So that's, I mean, that's geometric in itself, right? That's an invariant of a torsion group that you can see with your eyes. The sign is also an invariant you can see with your eyes, but sort of has to do with a different part of the problem, right? It's some Arf invariant of a characteristic 2 quadratic form. And globally, that's the only two invariants you see. So it's the dual graph is essentially the only one that has to do with the Riemannian metric of the curve. The other ones also have geometric interpretations, but that have more to do with the Picard group. I don't know if that's what you wanted or not.
Yeah, no, I think so. I mean, so you're saying sort of, but sort of it's too complicated. And so this is sort of the way to see that in some sense. Like it's, I mean, the more broad question, I mean, that I've never sort of quite thought of carefully, but is, I mean, how sort of the tropical story for curves sort of interplays with the combinatorial description of the moduli space. And I think that's sort of what you're saying as well, is that it's sort of, I mean, difficult to sort of spell out or it's a slightly different path to sort of see that sort of data of the dual graph or something. I mean, or
Yeah. Well, what I'm saying is once you've solved the problem of dual graphs, once you've imposed a dual graph, there's still more to do. And this more to do has very little to do with the dual graph or with the Riemannian metric. Well, it has a lot to do with the dual graph because one is given to you and you use it to get more invariance, but the problems you're solving have very little to do with the Riemannian metric.
okay, yeah, no, that's good. Okay, thanks. Yep.
More questions? Okay, I have a question, but maybe you have already explained. I'm not sure. Okay, so the log universal Jacobian is basically just the Diliman-Ford compactification of MGN. Is that right?
No.
So they're both like. So with the tropicalization, you're basically parameterizing the stable curves, right?
Wait, sorry, say it again. So
So is it like for the log peg knots? Is it the
yeah.
same as the Diliman-Ford compactification MGN bar?
No.
Okay.
The over MGN, you have a universal curve, and
Right.
this curve has a universal Jacobian, right?
Mhm.
So this is a family of things over MGN, of which every fiber has dimension G.
Yes.
And the same thing happens here. This log Jacobian, if you're over a smooth curve, is just literally the same thing as the Jacobian. And
Right.
if you're over a stable curve, it's a group that has to do with PIC, right? It's a limit of
Mhm.
quotients of PIC by discrete subgroups. So it's always
Yeah.
bigger. It's always of dimension G more.
Mhm.
And it's one sort of analog of the Jacobian.
Right. So you can't really find a correspondence between the boundary in the compactification you obtained by log geometry and the boundary of MGN bar?
Oh, sorry. So there's two things. There's a lot of logarithmic spaces in that story, and one of them is MGN bar.
Okay.
If you look at the space of log smooth curves, then that is really MGN bar.
Mhm.
With a log structure coming from its boundary.
Mhm.
It's just the Jacobian that's a different, bigger space. I thought you were talking
Oh,
about the
okay.
Jacobian.
Okay, yeah, maybe probably I just mixed it up.
But no,
Right.
MGN bar itself, it's really the same space, and you have a choice between seeing it as parameterizing stable curves or
Right.
seeing it as parameterizing stable log curves.
So if I give you a stable curve, can you tell me what the log curve is? And can you do it vice versa?
Yes and no. If you give me a log curve, I can definitely tell you what the stable curve is. That's the underlying scheme.
Okay, yeah.
If you give me a stable curve and you ask me what log structure you put on it, if I have a smooth generic fiber, there's no problem. I just look at my local equations for the smoothing. But if you don't have a smooth generic fiber, you have to make a choice of local equations. So the stable curve in itself doesn't come with a completely canonical choice. you could make some sort of universal choice, which is what you do for the universal curve. But you could choose any local equation you want at every node. And once you've done that, you have a log structure.
I see, I see. And then when you go to the root space, I think you said something like you can think of it as like some ramification of the curve over the marked points. So in the boundary, what does it correspond to?
So yeah, the fun thing that happens to the root space is imagine you've chosen all of your local equations at nodes, and you want to compute logpick. Well, that's very hard because you could always ramify even more than you've already done it at your nodes and get more line bundles on more blowups. So as you change these local equations to make them more and more ramified, logpick grows bigger and bigger and bigger, and it's never going to stop doing that. But for the space of roots, there's a maximum limit, right? At some point, this is a finite group, so at some point you have found all the roots. So if I give you a curve with a bunch of local equations at the nodes, and let's say all of the smoothing parameters, uv equals something, all of the somethings already have an rth root, then my space of roots is as big as it could ever be. It's not going to get bigger if I change my equations. So in some sense, you no longer need the log structure, right? If you start with local equations that are complicated enough, the space of roots just becomes a scheme, not more complicated than a scheme. But by demanding that these equations are complicated enough, you've passed to a root stack of MGN bar. Because on MGN bar, you have a bunch of length functions for your nodes. And if you want to demand that these are powers of R, what you're looking at is a root stack of MGN bar. So the way I interpret what you're asking is, why is this guy just a dumb scheme that has nothing to do with the logs once I root this one enough? And that's the answer, right? First, make the equations complicated enough, and then the roots problem becomes scheme theoretic.
Okay, yeah, thank you. Are there any more questions? Okay. If not, then let's thank Thibault again. Yeah. Thank you very much. And sorry for the delay at the beginning. Yeah. It's still in the morning in the UK.
Yeah, it's 10 now.
Right. So you have the entire day ahead.
Yeah.
Yeah. Have a nice day and maybe see you again in future conferences.
Likewise.
Yeah,
See
thank
ya.
you very much. Bye-bye.